So this year I thought I'd look at the difference between slopes, exposure. I called it aspect geography because aspect is what we call orientation in geology, some other trades, ecology. The aspect of the slope is the orientation. Which way does it face? And I selected the title north-south because that's in our label of the Civil War, north-south between opposites. Yeah. And it's really not just north-south. And I'll bring that out when we talk about the compass, because it could be slopes at any orientation. So you're not the only one here. We're doing a one-on-one.
I'm sorry.
I'll tell you about it. So I'm Glenn Minuth, for those of you who just came in, and I'm a retired civil servant for which you guys spent the last 33 years of my career there. And the first couple of years I worked in D.C. and St. Louis and Seattle. So I do instruction at Cochise College for history and mainly geology field trips and so forth. And I've been participating since the early 90s in Southwest Spain. So today we're going to look at the difference between slopes, what goes on in the nature between slopes. So this is just a quick overview, and I'm suggesting to you that the slope face presents some type of orientation to the sun. North-south, there's nothing really significant about just north and south. It could be any direction, complements, and I'll show you that on the compass coming up. But it creates a very different situation. There's different roles then for these slopes and local climates that are offered by the orientation. So those are usually referred to as microclimates because I'm just on a limited exposure in a selected area. So it helps determine these microclimates what types of plants will colonize the slope, and it also influences, of course, the animals that are drawn to the area seeking the resources of preferred foods, and then shelter also. So you have to realize that plants don't have much choice, or animals do. Plants are fixed in a spot. They have to take whatever nature throws at them, whereas animals can make adjustments, they can move. And that's certainly something that makes them better off than plants. The basic difference, though, between north-south facing slopes is the relative amount of sunlight intensity they receive. And that's energy. So energy is what drives the differences in these profound ecological situations that we see. And the situations we talk about today are going to be for the northern hemisphere, but it would be naturally reversed in the southern hemisphere. So this is some of the things I'm going to talk about: aspect geography, and then the concept for talking about slope orientation. We use a particular diagram called a rose diagram. So I'll show you some examples of that, how it's used for charting orientation, and then we'll talk about energy in the form of, here's an acronym for you, it's called insulation, not with a U here like you have in the walls to prevent heat transfer, but insulation means incoming solar radiation. So it's just the incident radiation from the sun on the earth. And we can measure that with pretty cheap instruments now that are called pyrometers, and you can calculate, for instance, how much energy in terms of calories intersects these Earth in a square inch. So I'll put a square inch down. The pyrometer tells me, gives me that measurement. And then I'll talk about soil. Of course, by the way, that's determined, the insulation is determined by the duration, how much the sun stays on an area, and then the incident angle. Is the sun at a steep angle or long? The pedology is the aspect of soil. So a pedon is soil, and logos in anything. Geology is the study of. So this is a discipline within soil science that looks to look at the evolution of soils and characterize them. I usually do that by digging a soil pit and looking at the different horizons that come up. And there's a discipline of that called soil geomorphology. For instance, I use that as a tool when I did my graduate work to look at soils in the particular feature I was examining. And then soils
play a big role in moisture capacity, how much water they can retain, and then also with plants, there's evaporation and evapotranspiration, because plants are doing work, they're factory. Photosynthesize energy that comes from the sun, and then pull out what they need from things like water and so forth, and they give off, of course, carbon dioxide. So we'll also talk probably a little bit about the depth of soil profile. Soil profile is the horizons of soil, and then tree canopy development, the erosion potential, those will be mentioned. And then what kind of expected life forms occur with the orientations on the slope, and then cover canopy protection. Probably mention something about those. So aspect geography is employed, as I said, with different disciplines. I listed a few up there, like physical geography and physical geology. And the study of landforms, that's what I am, a geomorphologist. I started off as a cartographer for the federal government and map maker. So this slope aspect is also known as exposure, and it's simply the compass direction or azimuth, and how to use the compass, that a terrain surface faces when you're looking down the hill's fall line. So imagine you on a slope and you're looking down. We're saying, well, what orientation does this hill that I'm looking down face on the compass? So these direction, well, I could go through an example that the slope landform on the eastern edge of the Rockies. You can imagine that. Sloping toward the Great Plains is described as having an easterly aspect, so that's how you use the word aspect. A slope which falls into a deep valley on the western side and a shallower one on its eastern side has a westerly aspect, so it's a west-facing slope. So the direction of slope faces can affect the physical biotic features that are exposed on the slope. This is known then as a slope effect in ecology. And the aspect is also complemented, or it's paired up with another consideration, and that's the grade of the slope. How much does the slope slope? That's very important too, so surface grade. So aspect can ultimately serve as your compass. A person who spends time in the outdoors can really determine which way without a compass. They're pointing simply by or facing by studying the slopes, essentially the landscapes on the slopes around them. So although north-facing slopes and south-facing slopes may receive the same amount of precipitation, they may have the same climate, they may have some similar soil components, the slopes will ultimately look different. So now I wanted to get into looking at a tool called the rose diagram, and it's based on the compass rose. So there's a connection right there. You've heard of the compass rose before, hence there's a rose diagram. And I just wanted to go through the points of orientation on the compass, and we can look between north and east. And we call the cardinal directions these big letters here, north, south, east, and west. And then we have ordinal directions, so something like northeast would be an ordinal direction. And then the last is secondary intercardinal directions. And those are the ones that are in between them. So to see those, you have to look like east, northeast, or north, northeast. But I want you to know that's about 16 different directions. There's actually 32 points to the compass that are described by directions, and these are them. So you know north, you know east, you probably know halfway between is northeast, and you've probably heard of north-northeast and east-northeast, but between those, there's other nomenclature. So if we take this east one, this direction right here, it's generally east, okay, mostly east by north. Whereas this one up here is, this direction right here is north by east. And in between is north by north, northeast, and then north by north, and then northeast by east. I did want to point out that in the Alfred Hitchcock movie, North by Northwest, that's not a legitimate thing. So you won't see north by northwest southwest here. They just gymmed that up. I just saw that movie recently, and I went to the Black Hills, also in South Mount Fresh. If you've seen that movie, and those are involved. And the original name Hitchcock wanted to use was North to Alaska, and that didn't flow. But it was suggested to him by somebody else that they use North by Northwest. It just had a sexier tone, and so that's what they went with. And by the way, the movie was supposed to take them to Alaska. They never went to Alaska in the real movie, the final movie. So we've looked at that, and now I'm showing you for the first time a rose diagram, which is simply a display of azimuths. You can see the same directions that would be on a compass rose here. And then you add some value, and here it's color-coded. And if you look at this carefully, it's wind speed in meters per second. So you can color-code those wind speeds over here in the legend, and see that the highest wind speeds are in the brown color. But what the value of this is, immediately you can use your eyes to set and see for this location, and it happens to be a time frame of January 2000 to January 2005 for some sample location. Doesn't matter where it is for this example, but you can see predominantly the winds coming from the southwest component. It's very similar actually to what we showed you. So that's kind of two dimensions, two features. You get direction, and then you get magnitude of some quantity. The quantity here is what? Like the quantity we're measuring? Wind speed, right? Now think of this. We have a rose diagram, but we add a third dimension. This is a display that comes from a software package for cavers who want to do cave mapping. So it's got the compass rose, and what they're interested in is the direction of chambers in the cave, the alignment on the compass. And then they're interested in the length. So here it was meters per second. Here, these are distances of cave chambers, how long they are. And then we can see that in caves, from this, they added an additional axis, which would be coming out here, the z-axis for height. So or elevation. So cave chambers are not necessarily all at the same level. You have to climb stairs and go to a different chamber and climb some more stairs to get to another chamber. This is Fulford Cave and how it's been mapped with this software package. And you can see that it adds that third dimension. And you can see that there are trends available here. So what is it doing again? It's mapping orientation, the frequency of occurrence, and the depth, essentially, of the cave chambers. And from here, we can see that clearly that there's an easterly trend confirmed by the upper part of the cave diagram. See these arrows up here. They're in the upper part, they're high up, and they're going east. So a few more diagrams. I wanted you to get comfortable with them. The wind turbine industry uses this as a big tool in terms of where to site the wind turbines. So they're measuring wind. In this first one, they're measuring duration on a particular date, on March 21st, 2016. This was what the wind profile looked like for that day. Throughout the day, you know, the wind changes directions for different reasons. And you can see for most of that day, it was coming in from the southeast. What's in the center is whatever they want to put in there. In this case, they wanted to measure calm, because calm is what the wind turbine industry doesn't like, of course. So it's only 1% calm is what they happen to feature there. This is still the wind turbine industry, but now they're looking at average wind speed for a locale on the same day, and they're displaying the wind speed for each wind direction here, and the average of all this. And we don't have a scale for this. I mean, there should be a scale on here, but you don't see the scale. But the average is calculated to be 5.9 meters per second east. Yeah. Now, winds are always measured from the direction they come, so the east wind would be coming from the east. And that's important for people who fly. So we have a Tucson airport climate diagram that shows a wind rose. And you can see here that the wind is coming from the southeast and amazingly, large part of the time, other directions from the west and southwest. Not very often does it come from the northeast, for instance. Now that corresponds to what a pilot needs to know. And I should tell you that that's how they orient runways for a location. Planes want to take off into the wind, they want to land into the wind, always. Never want to tailwind when you're landing or taking off. So you can see that they took advantage of knowing this, aligning the Tucson Airport runway northwest, southeast. This is the long runway here. They have most airports have a cross one runway, and it's usually 90 degrees, so they get the other component. It's a much shorter runway here, up by the National Guard base. Passenger terminals where you hang out if you travel out of there in this area. So pilots, this is the actual airport diagram a pilot would use if he was coming into Tucson, who's not familiar with the airport. It gives things like runway length and a lot of other buildings that surround it are labeled in the field elevation. Quite a bit of information on an airport plate diagram. So my interest is landforms, and although I did not elect to study this feature, I wanted to consider doing that. I went a different route for my graduate research, but I did, for the Central Sierra Nevada, want to consider the cirque orientation preference in the cirque floor elevation. What's a cirque? Well, a cirque is a glacially carved out, excavated area of a mountain. And it's done by glaciers. So you see glaciers still sitting in these cirques location today. Cirques cut out an area by excavating year after year after year. It goes on for 100,000 years during the glaciation. A big half bowl, an amphitheater, there's different words to describe it. And they face different ways. Well, this is a slope thing. They want to face in the northern hemisphere, usually to the northeast. And if you measure the orientation of the cirques, you'll see that type of thing on some diagrams, rose diagrams over here. And then the other thing you're interested in, if you're a geomorphologist, is understanding glacial climates of the time. And we can look at the regional snow line as an expression of the cirque floor elevation. So this has been done around the world, but it hadn't been done in the Central Sierra Nevada range where I grew up in California. So that was my potential graduate research topic, but it was going to take too long. I could spend part of my life doing this research, and I selected another topic to get through part of it. But other people have done it, and this is Alberta, the state. Actually, they call them provinces in Canada. So you see that outline, and at different locations in Alberta, and none are specific in terms of the spot. They're just showing regions here, because they couldn't fit all the data even into the state diagram. They're showing you how cirques are oriented. And they're using this region with the vector mean direction and vector strength. So that sounds technical. Vector is something with direction and magnitude. So in this case, we're measuring the direction on the compass that the cirque is facing, that bowl faces the cirque direction. And then they're looking at, in this case, how many cirques face that direction. And you can see it's not a surprise in the northern hemisphere in our mountain ranges that you conclude that most cirques face what direction? North or east, or in between, north, northeast, that sort of thing. And it's amazing how very few are found on other slopes. This happens to be a similar diagram, but it's for the Kamchatka Peninsula, and these are based on several thousand cirques. Russia's a big place. I think they looked at 3,520 cirques for orientation. So that's a lot of measuring. And each one of these, see, then they divided up 3,000 and some cirques, 3,500 cirques, we'll say, into equal numbers, and they clumped them by data direction and so forth. So this is a clump of, 352 cirques, 352, 352, and so forth. Each one of these diagrams has 352 cirques of the total cirques. And then they organized them by how they faced, and that's what you're seeing for different regions. So just showing you some examples of how those diagrams can work. Now here's one that's for a more basic purpose, maybe more connected to what we're talking about today, and that is not only aspect, but slope, as in gradient, how steep the slope is. So we can show that and then portray it on this very colorful map by indexing it to what? The rose diagram right here. And then, you know, there's 3 different levels with 3 different color levels. So we call the hue, that's the type of color, you know, if it's yellow or purple, that shows the direction and aspect. And then these 3 levels indicate the saturation, the color. You see there's different kinds of greens here. That's called color saturation. Well, why am I mentioning that? Because they show you whether you're in, or in means right in the center, or out on the outside, or in mid-range. This is how the slope's calibrated. So immediately, if you have that little rose as a legend there, you know, pick out a slope and you can immediately tell from the color, saturation, and the hue which way it's facing, and how steep it is too. So the more pure saturations are the deeper colors here. These are the hills that are going to be steepest. For instance, this blue here, the steepest pointing to the southeast. So there's a ridge line here, and actually this is southeast. That's a terrain map tool. So I'm looking now in geology or in landform analysis, geomorphology and aspect, some examples that have been researched. So this is in the Mackenzie Delta. So this is talking about the Mackenzie River Delta in Canada, that there was disintegration by frost through what's called freeze-thaw processing, repetitive freezing overnight, thawing during the day of rocks and slope materials. So that's a freeze-thaw process, and in east-west gullies, they appear to be more intense on the north side of the gully. So we've got an east-west gully running this way. It has a north and a south side. This gully runs that way. And what they're reporting is the processes of freeze-thaw, which break down soils and so forth, and rock too, are more intense on the north side because there's more cycles of that going on. In the Jura mountains, those would be in the border of France and Switzerland. By contrast, there's a greater accumulation of debris. Debris is not garbage from man, it's slope debris. That by mass wasting, gravity transfer processes, material goes downhill. At the foot of the mountain, the foot of the south-facing slopes, there's a greater concentration of debris due to greater amplitude of temperature changes, which is talking freeze-thaw, and more diurnal freeze-thaw cycles. The Kenai Peninsula is in Alaska, and the south-facing slopes are steeper, more steeper than they are longer. They're highly dissected, that means eroded, cut down on the north-facing valley sides, where the winter snow lasts until June. The amount of sunlight and insolation, let's talk about that on the slopes. In the northern hemisphere, north-facing slopes. In latitudes about where we live, you know, between 30 to 55 degrees, which is much more than they receive less direct sunlight than south-facing slopes. Some of this might be obvious to you, but I want to put it down so that it's crystal clear. The lack of direct sunlight throughout the day, whether in winter or summer, results in north-facing slopes being cooler than south-facing slopes. So there are, it's possible, depending on the steepness of the slope and the sun angle of the season, there are some slopes that will never get touched by sunlight directly. You know, there will be light, reflected light hitting the slopes, but never any direct sunlight. So during them, on some north-facing slopes may remain shaded throughout the entire day because of the low angle of the sun in the winter in the northern hemisphere. So this causes snow on the north-facing slopes to melt slower than on the south-facing ones. And of course, that's opposite in the southern hemisphere. Near the equator and north and south-facing slopes are receiving about the same amount of light because the sun is not at an angle. It's the equator, the sun's usually most of the time directly overhead. At the poles, kind of the opposite condition. North and south-facing slopes tend to be either shrouded in darkness all winter long, or they in sunlight all summer long, with only slight variations between slopes in the spring and fall. Again, because of the incident angle of the sun. So I'm going to show you a number of text slides like I've been doing, and then I'm going to show you some pictures of slopes. So we got pictures coming, but I need to go through some ideas here. Precipitation. Now let's talk about rainfall. In Bell Day, and that's in the Russian plains, with a December through March average temperature of 7.75 degrees, registered at 2 soil depths. So they're picking up the same temperature, but they're picking it up at different soil depths on the north-facing slope versus the south-facing slope. So on the north-facing slope, to get to 7.7 degrees, and this is Celsius, you have to go 31 centimeters. On the south-facing slope, you only have to go to be 2 centimeters because of the energy, incident angle of the sun and the energy being collected there. So water stored in drifting snow was 30% greater on north-facing slopes. The result is the spring runoff amounted to an extra 50 millimeters on the north-facing slope. So snow will melt faster in the spring on south-facing slopes, and consequently, it leaves the moisture leaves the ground quicker than on south-facing slopes. So I want to talk about snow on slopes, and I've got different reasons for doing it. One is to give you an appreciation for the importance of aspect in the winter. If you happen to be a snowshoer or a traveler through mountains that have a snowpack, so we'll be appreciating the importance of aspect. The problem here is if you don't know north from south and you're in snow country, then you need to learn, because someone who doesn't know the aspect has missed one of the most important pieces of the avalanche puzzle. So on the side, I'm going to tell you why I'm talking about this too. Is I've been in the ski patrol, National Ski Patrol, for over 50 years, and I teach avalanche. I've been teaching avalanche since the middle 90s, so I teach avalanche courses, basic, advanced, and so forth. And we spend a lot of time talking about the difference between slopes, and I'm going to get into this for 5, 6, 7 slides, so that you can appreciate, again, there's things that are different processes going on different sides of the mountain. So we're talking about avalanches and the influence of aspect with respect to the most important considerations would be in mid-latitude. So we're not worried about avalanches in mountains on the equator or mountains in, say, Antarctica, but we are looking at mountains between 30 degrees north, if we're talking about the northern hemisphere, 55 degrees. These are mountains that will be subjected, depending on their form and the height and so forth, their snowpack, to avalanche occurrences. So that ranges, if you don't have an appreciation for latitude, between the southern U.S. border. Hey, that's about where we live. So we do have mountains, the southern Rockies coming down in the next state over. We do have mountains here that go to 13,000 feet in our own state, and we have avalanche potential at some of these locations. We've had avalanches. I've had friends buried in Arizona in an avalanche, believe it or not. So at equatorial latitudes, the sun goes almost straight overhead, so it shines equally on all slopes. So whatever impact is going to hit a slope is going to be similar on the other side. In the Arctic, the sun's too low, as I've just mentioned a few moments ago. So there's pretty much equal chances there. It just goes around in a big circle in the Arctic with the same intensity one time. So this is the Arctic spring aspect. It has some influence, but not nearly as significant as the middle latitudes. That's what we're showing here is the impact by labeling here through the latitudes when or where essentially avalanches should be considered as being important as a hazard. So if you look at northern hemisphere conditions, north-facing slopes, they receive very little heat from the sun in midwinter. South-facing slopes receive much more heat. That's what the diagrams are showing you over there. So therefore, the north-facing slope develops a dramatically different snowpack in terms of the structure and quality of snow, whereas the south-facing slope is going to be warmer and develop thin ice crust, because these ice crusts tend to grow weak. That is, the layers around them form near surface faceting. I'll show you what faceting is. Talking about snow crystals and surfaces of the crystals. You want to be careful not to assume that southerly aspects are safer. That's because they're warmer, people think, and you have less snow, people think, well, I can't get hurt on the southeast slope. But you actually can. They have a different kind of avalanche. How about east and west? East-facing slopes catch only the morning energy coming in from the sun when the temperatures are colder, while the west-facing slopes catch the sun in the warmer afternoon because it's going toward the setting position. So east-facing slopes then are colder than west-facing slopes. We're talking about the snowpack exposure to the elements. A cold snowpack tends to develop more persistent weak layers, and weak layers are usually defined as certain types of crystals that have faceted surfaces. So commonly, these are notorious as occurring as fragile weak layers. They occur as facets, just faceted snow, or something occurs on the surface called surface hoar. So I'll be showing you those in these pictures. This is surface hoar. It's one of the most beautiful things to see in the morning. It's formed overnight. If you're a skier, snowshoe, or something like that, this is wonderful to ski through. And here we can see that the next storm will bury that. And that's where the weak layer is. And we dig snow pits and then perform tests. And here's a test result of a slab that came out. It fractured on surface board that's been covered with another snowstorm. So here's the failure block. If you can't see what's going on here, this is sky and gray clouds right up here. This wedge right here. This is the snow surface, looking uphill. They dug a snow pit probably on the northeast side of the hill to explore the depth. They did a test and they fractured out a slab of this thickness. This is a glove right here holding it. But what he's done after the fractured slab, he caught the slab in the snow pit he did, fractured, and he caught it, and he turns it over. So this is the bottom, the failure surface. Now what do you see here are these faceted crystals. They form a weak layer. So here's another try a portrayal of showing the original surface hoar build up here, and then newer snow up here. This is the old snow surface down here. This becomes a weak layer. You're getting what I'm talking about? There are weak layers and strong layers in the snowpack. In very wet snow conditions, due to strong sun, so now we're thinking this is occurring on the south-facing slope. It's just the opposite of the dry north-facing snowpack. So these south and west-facing slopes produce more wet avalanches than the shadier north slope. So a wet avalanche has flow properties that are much different than a slab avalanche on the north-facing, northeast-facing slope. So during prolonged storminess periods or cloudiness periods, when the sun never makes it to the snow directly, it shines, there will be little difference between the sunny and shady slopes. So that's one time. Both slopes, north and south, are the same. And remember that in the southern hemisphere, of course, what I'm saying is going to be the opposite. South-facing slopes are going to be the colder slopes compared to the north-facing slopes. Well, why is this important? So this is my safety pitch. If you consider slope aspect with wind, it's extremely important to recognize the importance of wind, particularly the predominant wind direction in stormy conditions. Because wind transfers snow. Snow hits the ground by gravity, crystals hitting it. But as it's falling, wind can influence it. Even after it hits the ground, wind can actually etch the snow, transfer snow, and put it somewhere. So what it usually does is, if there's a predominant wind direction, you'll see wind putting or depositing snow on one face of the mountain slope. That's what this diagram is showing. And you end up getting a big snow cushion. You can develop cornices. I'll show you a picture of that, what you can actually build as a feature. People like to ski these slopes. The snow is deeper, the snow is better to ski. So here's some cornices right here. Somebody up on top. Of course, these are very dangerous because if they break, they can fall and they can trigger an avalanche and release a huge slab of snow. So you don't want to walk out on those because they are overhanging and your weight will fracture them. But what we're seeing here is avalanches out of the Utah Avalanche Center. And where do you think that is? It's Salt Lake, and it's at the airport. It's not up in the Wasatch Mountains, Wasatch Front, but it's at the airport. The last time I went there was at least 20 years ago. They use a wind, or a rose diagram, not a wind diagram, a rose diagram to depict where in this season, the ski season straddles 2 years, of course, 212 and 213, that's when the winter snows come. They use this rose diagram to show where the avalanches occur. And again, what are you seeing here? Avalanches are very preferential. They like the north and east, particularly the northeast slopes. This is where people like to go too. So this diagram looks at fatalities out of the Utah Avalanche Center. So he's got a region he forecasts for. He's going to go together, does it for the big avalanche checks. I don't think he does that anymore, probably retired. But this is the collection of fatalities on slopes. And it's very evident that it corresponds to where the avalanches fall. So that's why we're concerned about educating people on the difference between slopes when you go out. Here's another way to portray deaths in a more detailed way. It's easier to see, I think. And they're looking at deaths below tree line. This is in Colorado, by the way. The Colorado Avalanche Information Center has this data. Near tree line, below tree line, above tree line. So they're showing you that the inside is above tree line and the outside and below tree line. So where, if you read this, now that you know how these work, where are you seeing most of the fatalities? Fatalities are in just about all bands, not much on the southwest side. You were saying the fatalities are the northeast, but near tree line. So it kind of starts to answer questions of where risk can be assessed if you're going to plan a trip. So I'm still sticking with avalanches. I told you a little side trip off on slopes. Windward side of the slope, that's getting snow transferred from it. You notice that on the leeward side, those arrows are showing. And you can see this happening here on this ridge. See these trees are, this tall. This ridge isn't really much taller than a tree. Or some trees are even taller than this little slope right in here we're seeing. But we're seeing the slab at a continuous fracture all the way across. Snow falls down and builds up in piles. This is where people get killed if they were on this slope, even skiing, how they could be buried down in here. You'd be surprised how little of a slope people skied on and then ended up at the bottom of the hill. Look at the difference between slope exposures here. Remember when we talked about a slope being totally in shadow for the whole day? There's an example right there, a very sharp ridge. This side of it is exposed. Good slab fracture up here. That snow runs down some distance. Here we see evidence of snow transfer. This side being etched, being deposited over here. That's probably where these guys would like to ski if they are on the skis, like you see. But there's a hazard here potentially for slab avalanches. So you have to know how to evaluate the terrain, evaluate the snowpack, and to do that out there in the field. On this trip, these people should be digging snow pits to evaluate for reef layers and so forth. But they're at least not on the slope, they're surveying it at this point. and then look at a big pullback picture of all the terrain features that could be a problem for avalanching, and then look where the avalanches have occurred. I see fracture lines that run right up. I should use this laser pointer. This is not working. I'm pointing at myself. If this was a gun, I'd have killed myself. Okay, so you can see extensive fracture lines right here. And that means the slope is avalanche. It's lost snow, and where did it go? It flows downhill. Do you see the deposits right down here? These are places to avoid then wind-loaded slopes, the leeward slopes. And you can see that the skiers didn't come down those slopes. At least there's evidence here for a lot of ski tracks in the wide, unsupported slopes right here. They stayed out of gullies. They stayed out of the cliff bands in this case. I just wanted you to see that you have to take a big look sometimes before you do things. I'm going the wrong way.
So when they take cannons out,
Yes.
this is what they use to decide where to shoot the cannon to.
Yeah, if this was a ski area that had avalanche hazards, and we have many of those in the United States, every morning the ski patrol does an avalanche run. They may use cannons, or they may use charges that are hand thrown. Some of them use what essentially look like little trolleys on cables over a particular slope. They decided to invest in a trolley system, a little cable like a clothesline, you know, the old style clothesline. You reel out a charge and drop it. Or helicopters throw a charge out that way. Or put the ski patrol out on an avalanche patrol. They handle explosives and then drop them over the tops of mountains and so forth. So that's to create a vibration force to do that. There are other methods to do it that are more dangerous, and that's called ski cutting. We've done that before, where you try to weaken a slope by skiing across it. You have to be careful and understand.
This is the new hire,
Pardon me?
the newest hire that does that.
He's got to learn, right?
Yeah.
No, they take that seriously, because if you don't know what you're doing and don't have a place to ski out, if you fracture it, you can become part of the slide itself. So I wanted to also talk about not only wind loading the slopes from the predominant wind coming over the top of the mountain to the leeward side and the windward side, but there's also localized winds that occur that are side or cross-loading the slopes. So they create things called a slab channel. You know, the wind might be forming a cornice up here. There's evidence for that. That's the predominant wind, but also there's evidence for the wind transferring slopes in this gully and the wind depositing it on this side of the gully. So people like to ski in gullies for certain reasons, and I'm just showing you that there can be wind loading and creation of slab channels. That's what I'm seeing here. You can almost see the overhang here in this particular one. Effects of rainfall on slopes. The amount of rain that falls on a slope to be taken up by the vegetation, that will be taken up by the vegetation, is determined by how steep the slope is. That's one consideration, and whether it faces north, the aspect itself. So on north-facing slopes, the vegetation canopy and litter that's on the ground breaks the impact velocity of precipitation, allowing slower percolation and runoff erosion. That's on north-facing slope. That's the vegetation canopy or the layer of say the forest floor. That's more developed, the trees on the north-facing slope, so it offers more protection. Rain, of course, would naturally run more quickly off steeper slopes and does not have time to be taken up by plants. And rain falling on less steep inclines stays in the soil longer and is utilized by plants and trees. Generally speaking, it results in larger plants colonizing the slopes with a higher hydration need. So if you're going to have larger plants, you're going to need more water. So that's where you want to hang out if you're a plant on the north-facing slope. Slope aspects can figure into this, where vegetation on the south-facing slope in the northern hemisphere has less time to take up water. because it's the drying effect of the sun. So that's where you're going to see marked differences, especially when we get to the pictures, slopes. So still talking rainfall, if you've got less than 20 inches of rainforest, give way to grasses, and when it's less than 15 inches, grasses give way to just shrubs for the most part. When it's less than 10 inches, shrubs are widely spaced, as in the desert. You think of creosote, spaced in this region at certain distances apart, or mesquites or something along that line. So they don't want to compete with each other. So as a result, there's increase of weathering on certain slopes, like the north-facing slope. They have higher clay formations. These are smaller particles on clay. Also clay, there's a thing called a clay mineral in addition to the clay's size of particles. So in geology, there's two different types of clays. One is particle size. Clay is the smallest particle we can visualize in the microscope. And then there's the clay mineral. There's an assortment of clay minerals. So we see those occurring more on north-facing slopes. And that permits more weathering and soil moisture retention. Clays hold water because at the very small molecular level, the forces, the electron forces attract things like water. Certain clays do. E-horizons, you may never have heard of that, which we call the summer alluviation, and you may never have heard of that. Simply means leach layers in a soil profile. That's an area where minerals have been removed. It's usually a different color than the soil around it, because why? Things have been removed. What's left is something that looks different. So they're less common on north-facing slopes. Now you'd think there'd be more leaching since there's more water, so that's almost a logical prediction. This should be just the opposite, and it's not for some reason. The other thing is on north-facing slopes, the exchangeable basis is chemistry, soil chemistry, base content of certain minerals called the CEC, capacity for cation exchange, CEC. And in chemistry, that means the ions, like some of the metals, or sodium and so forth, potassium, those have an exchangeable capacity as minerals to move around in the soil, be transferred in the soil. So that happens better on north-facing slopes. That's all I'm saying. What's that do? When you make available bases, it contributes to more luxurious vegetation. So because of higher humus concentrations on north slopes, these cations, here's some examples of calcium, magnesium, potassium, thus are prevented from being leached and are retained in a form available that organisms, higher plants can use them. In some locales, there are patterns of soil differences related to differences in aspect, of course. The depth of soil on a slope, whether it faces north or south, solely depends on the steepness of the slope. So gravity is playing in that effect. The steeper the incline, the higher the rate of soil erosion from rain runoff. And then soils on steep slopes are primarily made up of rocky fragments because pieces of the lightweight organic matter, such as leaves, have already washed away, and they can decompose into the soil. Slopes that have a gentle incline tend to accumulate deeper layers of this organic material, which is good. Northern hemisphere soil on south-facing slopes dries out faster because the sun on it. So it's also warmer. Soil temperature is important for seed germination. But consequently, it's no surprise that the soil profiles are more extensively developed on north-facing slopes. The slopes relationship with the local prevailing wind will also affect the soil makeup. So a slope facing the leeward wind will have more organic material because it's been deposited. Just like the snow, if you're moving stuff in a wind, a high wind, like we had last night from downdrafts out of thunderstorms around here, you'll transfer material. It might be leaves, it might be weeds, it might just be clay particles and so forth. Whereas the slope facing into the windward side would have less surface soil. So soils with a prevailing windward aspect will typically be shallower and often with more developed subsoil characteristics. the pictures. So I will tell you that steeper slopes with equatorward aspects tend to have soil organic matter levels that, and seasonal influences that are going to be similar to level slopes at lower elevations. Whereas poleward aspects have soil development similarities to levels at higher elevations. So that's that deal where if you go up in latitude, you experience a certain order of plant transitions. Or if you go up a mountain range, you get a similar limestone transition of plants and animals. Organic matter is oxidized more slowly on the north side slopes, and there's the presence of more humus on north-facing slope. So that reduces the effects, the humus content reduces the effects of freeze-thaw, frost action in the top layer of the soil. I think I want to move along and get to some pictures here, so skip ahead. We'll say that the pH level is interesting. It will change on the north and south facing slopes. pH is the acid base amounts, and that's been looked at in different studies. And the research study here is looking at 63 species of plants and looking at their distribution with respect to elevation on a mountain range. And they found that soil pH increases, it becomes more basic, more steeply on the north than on the south slope. And they observed a shift in slope preference from north to south for the plants, at least in part, and that can be explained by the soil pH differences. So there's a pH difference in the picture by the researchers. I put in this ridge line because they put in this stuff that's supposed to simulate a ridge, this gray area in gullies. I'm not sure if it's going to be clear, so I made a ridge line there and said this is the ridge line ornamentation. What they were doing is showing for different plants the distribution on a south slope versus a north slope. And you can see just from the colors that, for instance, there's more of these purple type of plants, this plant right here, than on one slope than on the other. It goes that way for the other plants. So when you're out in nature, one can be looking at the differences of plants. I did want to mention carbon. I have about 5 slides on carbon to nitrogen ratios. This is something you can't observe. You can only see the indirect effects. You have to have a mass spectrometer probably on the hill slope with you. But it is a ratio of the amount of carbon molecules or atoms essentially to the amount of nitrogen. And these ratios are important for plants. For instance, their photosynthesis. There's different types of photosynthesis right here. And these ratios are retained by plants that do certain types of photosynthesis. The ratios in marine environments like plankton, for instance, are 4 to 10 in this range to 1. So it means 4 to 10 carbons to 1 nitrogen. But we're concerned where we live. Terrestrial forms have much higher ratios. So vascular plants have ratios of 20 to 1. So scientists will look at that to understand that the lack of cellulose has a big complicated little formula here. Has a greater number of proteins, in the algae than in cellulose walls of, say, the plants. Algae doesn't have cellulose, and so it has less carbon. You can see carbon has 6 molecules in this formula here. Cellulose, for instance, has this complex chemical structure. I just wanted you to see the shape. And at every point in these similar rings is a carbon molecule. So that's where the carbon comes from in plant walls, cellulose walls. I want to skip through carbon nitrogen ratios, just for the sake of time, and get into slope aspect on plant communities. We have distributions that vary widely depending on what slope you're on. You know that in the northern hemisphere, warmer south-facing slopes will green up sooner in the spring. They stay greener longer in the fall, and they tend to be drier than north-facing slopes. Some plants that tolerate these hot, dry conditions, which depending on the region you're in, might be oaks, few pines, and I'm talking our region, drought tolerant shrubs and grasses. They grow quite well on the southern slopes if they're natives. A few feet away, a cooler, moisture north-facing slope with a gradual incline may be dotted with close mixed hardwood or conifer forests and shade-tolerant wildflowers. North-facing slopes, this is important, permit seedlings to survive with more favorable ground temperatures. And looking at life forms of the plants, trees capture indirect sunlight a lot better than, say, the life form of just grass on the ground. So there's different plant communities, of course, that pop up, and we're going to start looking at them, and you're going to find out that if you look at the different slopes, there's going to be a certain species frequency and a certain stand density. So how many species you have, and then how dense is that species occurrence. North-facing slopes are dominated by more species in a dense fashion. South-facing slopes have fewer species and are more sparsely dispersed. So ultimately, the species of plants found on south-facing slopes are more drought tolerant, while the north-facing cousins are less skilled at surviving with low water amounts. In Colorado's, we're going to be looking at pictures here shortly. In Colorado's southern mountains, the north-facing slopes are full of large evergreen trees, and the south side has more shrub-like vegetation, like sage. And we're looking at pictures here from the Pinell Mountains. This is Mount Colorado, and the difference in slope orientation just 100 miles north of here, perhaps. And even over in Chiricahua National Monument, I put in these sun rays to help you know, see which slope the sun's on the most. This is the south facing slope in Rhyolite Canyon in the Chiricahua National Monument. This is the north facing slope. Good example of different vegetation. Now here's a study that looked at several abundant species in California on north and south facing slopes, and they looked at the average percent cover of several of these species. The bars, like this, you'll see on the diagram, beta bars, here, they represent one standard deviation. If you don't know what that is in statistics, it's just a way of looking at the distribution of data. So you can see that some of these, the bars are so tight, you can't see them because of the large dot. That means the data is really concentrated that they collect. I dimmed or lowered the font on information that's not real important, because I wanted you to see that to determine what they wanted to do was determine the percent cover, ground cover, varying depending on the year, the slope, the aspect, or the interaction between the two factors. And the species with the highest overall cover for each functional group are presented here. So pick one, doesn't matter which, these are common flowers, vegetation in California. Each graph has a timeline of a few years, and each graph has a percent ground cover of that flower covering the ground. And so they looked at that, and by the way, the most important thing is north versus south facing slope. Black dot is north, the open circle is south facing. So you look at those two slopes and see if there's any trends between the species and so forth. There are some radical things like you wonder what happened to the caterpillar or scorpion weed here in year 214. That's this big trend. The other trends kind of track, show you that in some cases there's a flip-flop on north and south facing slopes, and you wonder why that plant did better on one slope over the other. So let's look at some pictures. I like the pictures because they show it best. Again, I'm putting in these sun rays up here just to show you the orientation. I think that's an excellent picture, but I don't know where it was. It's in a federal soil publication. They don't say where it is. One thing that happens is that tree lines are determined by slope orientation. And you can see that on one side of the slope, the sunny side, the tree line is much higher than on the northern slope. Eastern slope. So the northern hemisphere case for the northeast aspect reduces evapotranspiration. That's what plants put out, transpire, There's greater soil moisture levels, improved plant growth, biomass production, that is plant matter production is a higher carbon level because of that. Improved drought survival rates for those plants, and increased solar radiation on southwest aspects increases the evapotranspiration. So on the other hill, we're losing moisture is what that means. And there's decreased biomass production, and seedling survival rates are not as good. And if the plant makes it to become a plant, the drought survival rates for the plants are decreased because of the stress on them. Look at these hills here. One over on the right, just to start there, shows a big contrast in the Santa Monica Mountains of California, where you see coastal scrub on, there's no big trees here, by the way, of course, it's big shrubs, massive shrubs. So the slope on the left side is north facing, that's mostly ceanothus that's dominating it. And then if you look at the south facing, the right side where I put the sun, it's a artemisia and a yucca type plant over here. So artemisia is sage, it's sage type environment. On the left over here, we're looking up in southwest Idaho, northeast of Mountain Home, and you're seeing the effect of forest on the side that's away from the sun versus the exposed slopes. It's very apparent. How about up on the upper left? Some good examples. And then these three pictures here will show you what's going on in the canyon and snow country. It doesn't have to be at the highest location, but you'll see scrub oak here. But what you can't see is that the experience is the snow depth here is very shallow on this exposed slope. Again, we're looking at the same area, looking at that gully, at the melted out slope. This photo is taken in the shade of a large ponderosa pine tree. You're looking in and down the gully, seeing the scrub oak side on one side. This is a huge contrast here. I don't have to put the sun in to show you because you can see one side's lit up, one side is in shadow. This is actually a glacial red. It's the edge of a cirque, very sharp ridge. And we see that this is in a national park, the Southern Alps, Codian Range. So on the right side of the ridge is what's called the Uppak, the mountain slope. It receives little sunshine, and that one is especially facing north. And it's plunged into shade, and that shade protects that thin layer of snow into the night. And you can see that there's a balance then between these two things in terms of energy as it's expressed on the surface. This is the Bogus Basin ski area north of Boise, Idaho, up here on the ridge. You see antennas and so forth. Down from there are slopes that are a good example. Over here on the Carissa Plains in eastern San Luis Obispo County, look at the difference on one side of the gully to the other. So I want you to now consider not plants but animals. We've had a good idea of what plants can do. Animals are different, they can move around. So there's deeper soils on north-facing slopes, and they provide these conditions that attract micro and macro fauna. So a microfauna is something we really can't see with the naked eye in the magnifying glass or microscope. And what I'm showing you over there is mycorrhizae, these filaments that are fungus that are underground in the soil. And those are very important to breaking down the elements. I could show you the difference on north and south slopes, so how many of you would be interested in looking at these filaments on the slopes? So I'm picking naturally something you're more familiar with, megafauna. It would be a deer, something big. You've seen deers, you know what they are. So that's why I put the deer picture in there. And we're going to now look at slopes differences from thinking like a deer. So this is the introduction. Winters are awfully brutal on deer herds, but most whitetails can tough it out and survive. Their instincts, they're able to calculate, and their decisions they make guide them through these dreary days, and they often are led to bed down on south-facing slopes. The reason why that happens is a little more complex than a simple direction on the compass. I've been telling you compass directions and so forth. Let's look at how a deer thinks. Say they seek windbreaks. They don't want to be exposed to the elements. So nope, I'm going the wrong way. We're toward the end. Something's going out of control with me at the helm. So I was telling you they seek windbreaks. They don't like the cold fronts that come through with the bitter temperatures and the high winds come out of the north and the northwest through a part of the United States. So they naturally would bed down on the south-facing slopes. That helps block some of the razor sharp and cold that they'd be exposed to, and thus they can conserve calories, less heat loss. That aside, regardless of the weather, mature bucks generally prefer to bed on the leeward side, the downwind side of a ridge anyway. Deer usually bed along the top third of a ridge in hill country, where they are prevailing winds bring the air over the top of the ridge to them, and then thermals rise from the valley below, if we're talking about daytime conditions. And this allows the deer to smell potential threats from two directions at once. So you've got wind coming over the top of the ridge and then convection, thermals coming up. So these south slopes are warmer. In the winter, the heat rises in the east-southeast and sets. The sun I'm talking about in the east where it rises in the east-southeast and sets in the south-southwest, because of that the south-facing slopes receive both the first rays of sunlight and then the most sunlight throughout the day. So depending on the latitude, the southern slopes receive as much as 40% more energy from the sun in a given day than the northern slopes. So that difference can range from a few degrees to as much as 10 degrees. So that's substantial for survival for them. Because they're warmer, they typically hold less snow, these southern slopes. On the other side, they'll actually have a longer growing season, meaning there's more to browse on, both later in the winter and during the early spring. The deer know this, and they certainly take advantage of that whenever it's possible. So in the big picture consideration, we're talking for the hunter or the observer, the animals, or for the researcher, whoever you are out there. There are other factors to think about when you're encountering late season bucks than the nearest south-facing slope. Not every winter is cold, and during the warm spells, the thermals benefit on the south-facing slopes are diminished a bit. So thermals are really big here in the summertime frame. So you'd want to focus first on the leeward ridges, whichever direction they face. And of course, the overall landscape habitat needs to be good. With deer, food is king year-round, especially late in the season, before the winter. Deer aren't going to just bed down on the south-facing slope if there's not cold and clean there. They need cover too, the bedding cover too. Early successional habitats are always preferable for bedding, and so if there's a thick clear cut nearby, that's where you want to look. So as we close out here, my favorite place to see a great contrast between north and south, or east and west slopes, would be you drive out I-10 to the east, and let's say you're going towards Safford. You turn off 191, this is Safford, and you take 191 and you go out toward a little settlement. It's got a drive-in theater, that's how you know you're at freeway. And if you went left there on 191, you'd go to this big excavated area, the biggest copper mine pit in North America. Well, we're traveling today up Highway 78 over Mule Creek Pass over to Highway 180. It beats going up this road. This road has like 419 hairpin turns, whereas this road, 180, if you could go all the way over to Mexico and want to go north, it's a much quicker road. So anyway, I'm showing you this to show you where the great contrast is that I like. It's like night and day when you reach up these areas. Here's some pictures of this terrain going through the hairpin. You notice this terrain is not vegetated very much here. That's what you're looking at. It's got grasses and shrubs. But up here, there's pines where I've drawn the line in. But right here on the road, you don't have to drive off the road to see this. As soon as you break through the pass, man, it's ponderosa pine forest. It's a great place to see things. So just summing up, the aspect can have a strong influence on slopes temperatures because of sun angle. We talked about that throughout. And the aspect of the slope can make significant influences on the local climate. And accordingly, in the northern hemisphere, a south-facing slope is going to be more open to sunlight and warmer, and generally will be drier. So these things are evident in where people settle. So in the Swiss Alps, you can see farming is much more extensive on south-facing slopes. Of course, animals will take advantage of that. As we said, in the Himalayas, you can see the same effect on south-facing slopes because they're warmer and wetter forested. And north-facing slopes. So I did want to let you know that this weekend we're going to take a geology field trip. This is part of the free program. It's on Saturday morning, listed in the schedule down here. This is an excerpt from 8 to 8:30. We'll meet here in one of the rooms. I'm thinking it's this one, but it could be the one right outside the door of the library in that direction. And will be a half-day field trip, so we only go to 12 units. I'll be taking part 2 of the Ancient Seas field trip. Last year we did part 1, which was from outside of Bisbee to the intersection of Highway 80 and 90. And that's where we'll begin our field trip. Although it begins at the college, I'm saying I'm going to start showing you things at Highway 80 and 90 junction. It's a car convoy, so you can use one of the vans here because it's a free trip. You just take your own car. And we do roadside geology, we don't hike. We're looking at the Paleozoic era because this means big limestone deposits during this time frame. So I'll be talking about fossils, showing you fossils, different limestone layers, and I'll have geology maps there. So that's Saturday, starting out with a half an hour little lecture organization time in one of these 2 rooms here. On tomorrow, actually, I'll be talking from 12 to 1:15 on how birds work. And this is the title slide, so it's going to be about structure, meaning skeletons, the bare bones of the skeleton. So it's great to identify birds and so forth, but it's even more enriching to me to understand how they work. So I'll be starting with the skeleton, and we'll see what goes from there in terms of other systems in future years. I'll show you my plan. So that's where I wanted to end. If you have any questions, let me know, or comments on anything we talked about. Okay, then maybe I'll see some of you tomorrow or on Saturday morning.